Good morning, ladies and gentlemen. My name is Jervinska Anastasia, and today I would like to present to you my solution to the problem number 9, Sultry. At first, let's look on the problem. If you look along a heated surface, for example, if you look along above the burning coal, the image often appears hazy because of density fluctuations in the heated air above the surface. Can one determine the temperature of the surface using this effect? What is the precision of such a measurement? So I've divided my presentation into 4 parts. I'll begin with qualitative explanation, then I'll go to the theoretical description of our situation, then I'll present you my experimental step, and then I'll discuss the precision of my method. At first, let's try to look on our density fluctuations in our own eyes. We used the shadow method. We have lamp, we have stove top, from which the flows lifted, and then we have a screen on which we can see the shadows of these flows. Here you can see the pictures. So what we can see? We can see the stovetop. It hits the air, and the hair above the surface is cold. So the heat air have the density less, and it lifts. On the pictures, you can see that the convective flows have stochastic nature. Now let's go to the qualitative model of my effect. We observe the warmed convective flows where the refractive index changes because of the temperature increases. On the slide, you can see the dependence between the refractive index and the temperature in the flow. You can see that it is interesting that the refractive index in the flow is less than the refractive index in the outer space. We can compare the flow with a little lens. The beam of light reflects in this lens, and you can see from the picture that on the edges of the flow is the field of light, and in the center of the flow is the field of shadow. You can see this in our pictures. Really, you can see that in the center the flow is dark, and on the edges it's bright. Now let's describe our flows if they're laminar or they're turbulent. We can see that the Rayleigh numbers, which are the analogy of Reynolds numbers for the convective flow, are very high, so we can conclude that there is strong turbulent convection. For the description of strong turbulence, we can use the model of vortex changing. What it is? We have one big vortex, which divides into smaller vortices because it's unstable. So the process continues until the Reynolds numbers will be small enough to let the viscosity destroy the vortices. We can conclude from this model qualitatively that with the increase of temperature, the characteristical size of vortices decreases, so the difference between two close points in the flow increases. Here you can see the computer modeling, and we can see that with temperature increase, the length scale of the vortices decreases, and we can use this for estimating the temperature of the surface. We decided to use the Kolmogorov-Tatarsky model to describe the turbulent flow. We used the structure characteristics of the flow, which are based on the law of 2/3 by Kolmogorov, and the structure characteristics describes what is the difference between two closed points of the flow in the turbulent flow in average. You can see that there is a quite simple relation between the structure characteristic of the refractive index and the structure characteristic of the temperature. So let's begin with describing the structure characteristic of temperature. We can use the model of free convection. We can use the average gradient of temperature in the flow. And we can get with easily derivation the formula which connects the structure characteristics of temperature between the temperature of the surface. Of course, the structure index of temperature depends on the height from the surface. So we can suppose such a method of measuring the temperature. At first, we determine the structure refractive index, for example, by zeta of laser ray. Then we express the structure index of temperature from the structure refractive index, and then we estimate the temperature of the surface using the model of free convection above the surface. So, to get the structure refractive index, we can use the zeta of ray in the flow. On the picture, you can see that, of course, the ray deflects in the flows, and there is some deflection, some variance of zeta. Let's see the relation between the dispersion of laser beam zeta. You can see that we can simply calculate the structure index of refractive index from measuring the average deflection of the laser ray from its undeflected position. And now you can see our final result, the relation between the temperature and the dispersion of zeta. So we can measure the dispersion of zeta, and then by substituting it in this formula, we can simply calculate the temperature of the surface. You can see that there is the dependence from the heights above the heated surface, and from the temperature of outer space, and from the size of the surface. Here you can see our experimental setup. We used a laser. We used the stovetop. We can regulate the temperature of the stovetop. And then we measure it by our method. In such a way, we can describe the precision of our method, the difference between the real temperature of the surface and the temperature which our method gives us. Here you can see the animation of laser zeta for different temperatures. You can see that for high temperature, the jittering has bigger frequency and bigger magnitude. Here you can see how we evaluated our data. We get the camera report, and we get the dependence of the geometric center of the laser ray from time. Then we define the geometric center of the laser beam for each ray using the Adobe Photoshop. Then we write its coordinates, and then we calculate the variance of zeta. And then we substitute it in our formula and calculate the temperature of the surface, of course. Here you can see the measurement of temperature for different settings of the setup. Here you can see that blue points are the measurements with thermocouple, so we can say it's the real temperature of the surface. And orange points is the measurements with our method. And you can see that they are quite close. The difference of them for the biggest temperature is about 20%. by the first point, from the first point, we can see that there is, of course, no deflection of laser ray when the temperature of the surface is equal to the temperature of outer space.
2 minutes.
Here you can see the measurements of temperature for other settings of this top, and you can see that there is also quite relatively high precision. And now let's come to the conclusions. We explained qualitatively the haziness of image. We use simple statistic model for determination of the temperature of the surface. We suppose the method for measuring the temperature of the finite surface. Our method could be easily transformed for measuring the temperature of infinite surface, for example, the desert. And we got quite good accordance of results obtained by measuring with the thermocouple and by our method. Thanks for attention.
Opponent, you have 2 minutes for questions, technical questions.
Thank you for this presentation. I have some technical questions, especially about the scales of your setup. So please, could you show us once again the image when you show the deflection sigma before it? Yes. What are the typical lengths of the plate, the heated plate, please? What is?
Please, it's written, it's 20 centimeters.
Okay. And so
Its diameter.
And so then you let the deviated laser beam propagate along 5.5 meters. That's it?
Yes, yes.
Okay. And could you please come back to the slide with the two laser beams moving, please?
With the...
you have your two laser beams which are perturbating and we see them moving. Yes, this one. So what are the typical sizes here from your image and from the laser beam projection?
The size of each picture is 3 centimeters.
So the picture is 3 centimeters wide?
Yes.
And what are the, I don't see, which amplitude did you measure actually here?
The amplitude of G-string, the laser ray. We measured it with Photoshop. So we measured the position of geometric center, and we measured its deflection from its initial position.
Yes, but what typical deflection here from, I don't see. It is, you have 3 centimeters, and so you have around 1 millimeter of deflection.
And for little temperature, it's about 2 millimeters, and for high temperatures, it's about 5 millimeters.
Okay. And what about the frequencies of these movements?
The frequency of these movements, it's about...
Thank you. No time.
Fine.
You have 2 minutes to prepare. On décale tout. 1 minute. Thirty seconds. $20. Okay, you have 5 minutes.
So, hello everyone. I am Jeremy from the French team of the ENS de Lyon, and I am going to build the opposition to the subject that was presented by Russia, Sultry Day. So, first, let's begin with the strengths of the reporter's presentation. So, the setup seems relevant to the question because they look to density fluctuation. That's a good point. They also use shadowgraphy to visualize in which regime their measurements are done and in which area of the heated air. So they are not in the thermal boundary layer. That's a good point. They have also done an original image analysis because what they show, the data they extract from their analysis are not really visible to the naked eye. And that's a good point because they have a laser spot diameter which is an order of magnitude over their mean square displacement. So they did a good job to extract this mean square displacement. That's a really good point. But we also noticed some possible improvements. So first, and I would like to come back on this image analysis, considering the center of your beam. Why don't show us some plot of the center of the beam to see if there is, so you see in an XY graph, for example, to see if there is an asymmetry between the standard deviation in X and in Y. What are the typical standard deviations in both directions? And maybe spectrum analysis, because you don't talk about the frequency of this variation, and this is, I think it might be interesting. Then about the precision. So what about below 100 degrees? Because I know if I come back to your picture and my picture in the desert, maybe the typical temperatures are more under, actually it's true, they are more under 100 degrees than over. So what about this range of temperature? How to optimize the setup considering that you have actually relatively low standard deviation according to the size of your beam. So maybe you could optimize your setup to increase the standard deviation. So especially here, what becomes standard deviation on the x-axis, for example, and maybe on the y-axis if you have some different answer. If I multiply the size of your plate by 2, for example. What is the scaling of this kind of modification? And same question about the distance between your plate and your screen. What happens on your standard deviation that you observe it if I multiply this distance d by 2? So this will be discussed further. About the theory, so you use the Richardson cascade and Kolmogorov model. It's the classical model of turbulence, so it's quite accurate and adapted. The interest of this theory, you wrote a lot of equations, but there was no characteristic or length scale for the vortices. So maybe it would interest me to know a bit more about this. And also a characteristical length scale for the density fluctuations, because is it the same as for the vortices? Is it lower? What about it? We'll discuss it, I think it will be very interesting. And also with this model, so what are the numerical, maybe a numeric value at least an order of magnitude predicted by your actually quite adapted model? Then, if I consider the question asked by EPT, you quite well answered to the determination of the temperature of the surface, but only above 100 degrees, as I already said. And about the precision of such a measurement, you don't give us the precision of the temperature for a given standard deviation.
1 minute.
What is also limiting this precision? in your setup. So I give you two maybe ways to improve. But if you think to over limiting things, it will be very interesting to discuss it, and obviously how to improve these limiting things. And about the questions that I really would like to stress on in the discussion, how to measure the temperature below 100 degrees. So I have indicated times because I think it would be really great to discuss all these 3 points. Also, the comparison between your model and your experimental setup, because you show us some results, but no comparison with a model which is actually quite complete. And so which comparison could we have? And on the physics of your setup, which prediction on the variation, especially for this scaling, and which dependence of the sigma between the distribution of the optical index, the local temperature fluctuation, and the huge difference of temperature. Thank you.
Now we have a 5-minute discussion between the reporter and the opponent.
So you asked me how to measure the temperature below 100 degrees. So you could see that for the low temperature, for our laser, it would be quite difficult to measure the temperature. So at first, so the main difficulty is, I think, that it's the laser rays from the real laser are not really absolutely parallel. So there is quite difference between the size of the laser spot at the beginning and in the end. So and the deflections of the laser ray would be very little in comparison with the real size of laser ray. So we should improve our precision. At first, we should took the laser ray with quite parallel rays.
Okay, so you put it on the parallelism of the laser beam,
Yes.
which is limiting here to go below 100 degrees. That's
Yes, it's
Okay.
limiting.
Now, about the second point I stress here, which comparison could you make and why didn't you make it between your model and your experiments, actually? If you
don't mean
you-
these
you
graphics,
might-
really?
you might maybe switch.
Yes. So really, this is. Let's wait for the slide. So our graphs are the comparison between our theoretical model and our experiment, because we measure the temperature with thermocouple, and we measure the deflection of laser ray for this temperature, and we calculate our temperature from the
No,
deflection.
Actually, it is a comparison between two ways of measuring the temperature of the plate, but I don't see any theoretical curve here using the formulas derived from your model. So why is that? What would it tend to give if you plot actually here your temperature as a function of the standard deviation? I would have in the opposite. I would have done in the
Really,
opposite sense.
I
But
think it would have better sense. It would be more reasonable if we took the dependence if you want the theoretical curve, the deflection from the temperature, because the temperature, the deflection is the function of temperature, but not, of course, the temperature is the function of deflection, really. So.
But you have a formula actually in your model. Do you have a formula linking
Yes, of course.
sigma with the temperature?
Uh,
Why
it's-
not plotting it on your graph, just in order to compare if the expected evolution of one as a function of the other is the same that you measure? Because
Of
actually here
course,
the formula is quite hard to. Because actually, moreover, in your graph, you all plot
you
in
expected
TS.
you expected the maybe you expected the comparison between the theoretical estimated deflection and our measured deflection,
Yes.
really.
But
but
it is not done. Maybe we could move forward to the third point. Maybe we could come back after with the
Yes, yes, maybe with the review.
It might be interesting, but I have a third point to discuss. It is about the physics of your setup. So the projections, actually the scaling of your derivation is if I multiplied the size of the plate by 2. What, in your mind, would it give as your deviation? If I multiply the length of the plate by 2, will the standard deviation be multiplied by 2, square root of 2, 2 to the power of 2? I don't know. What do you think?
Let's go here. No. Oh,
You
please.
don't?
In my slide.
Yes.
Yes, it's here. You can see that. You can see from this formula then that if you took the constant temperature and you increase the size of the plate, for example, in 2 times its x, the refractive index would be constant, and the angle deflection would increase in square root of 2.
Okay,
Thank you. So now we have 2 minutes for technical question from the reviewer.
Okay, my first question, what was the ambient temperature during your measurement?
26 degrees.
Thank you. What is the error of thermocouple measurement?
The error of thermocouple, the error of measurements for the thermocouple is 1 degree.
1 degree.
But there is some point about it. We maybe discuss it.
Okay, thank you. And how far from the laser you measure the diameter of the beam?
We measured the initial size of the
Just
laser
after
beam.
the laser?
Yes, just
Okay,
after the laser.
Thank you very much. Question to the opponent. Do you think this measurement is precise?
Actually, which one? With the optical effect or with thermocoupling?
Optical.
Okay. I don't quite think so.
Okay, thank you very much. And
You are not interested in the physics.
okay, again, question to the reporter. What kind of equations are behind your numerical simulations? Are these Navier-Stokes equations or some other equations?
Simple Navier-Stokes.
Simple Navier-Stokes with all the terms, or?
Please. Please repeat.
With all the terms of the Navier-Stokes equations, or some simplified Navier-Stokes equation?
It's the program. It's the program with boundary conditions. It's the program for modeling the hydrodynamic.
Okay, thank you. And one more question to that: was your simulation 3-dimensional or 2-dimensional?
Really, I should precise. It's not my result.
Okay.
It's the result from the computer modeling.
Thank you.
Okay, thank you.
For the
Reviewer, you have 1 minute to prepare.
So once the time is up, we'll take a technical break.
Ok.
Time out, 1 minute.
Pardon? Pendant la préparation, oui.
Précision, je peux demander à tout moment un temps stop pour dire au jury est-ce que c'est ça les règles? Est-ce que c'est vraiment ça le rôle défini? Je peux faire ça ou pas?
Oui, oui, une question maintenant pour vous. Pardon. No. We are kind of very, very, very late. 20 seconds. Ten. Shh. You have 3 minutes.
Welcome, ladies and gentlemen. My name is Wojciech Rządkowski, and it's my honor to present Polish review to the problem number 9, Sultry Day. And regarding the content, first of all, we have to determine what hazy means and to observe some hazy image. And we think that it was partially done since you provided some imaging. However, the precise definition was missing. And then we should propose a method to measure the fluctuations and maybe introduce some scales. And here it was done because you proposed a method and the method works. And then we should talk about the precision of measurements. And we not really think that it was included, some numbers regarding the precision. And to the reporter, we really enjoyed the good qualitative explanation, which gave us insight into the model. And it was really good that 2 experimental methods were introduced because we can compare between them. And also the setup was clearly described, letting us understand how the measurements were done. And also we really enjoyed the shadow imaging of the phenomenon, which gave us insight into the nature of the turbulence. However, the presentation would be even better if some assumptions behind the Kolmogorov-Tatarski model were introduced, and if some and if the parameters that are important when we move from the lab to the real life are mentioned, such as wind. And also, the task stated that we should concentrate on precision, and it was not given. However, it's important for every measurement device and for this task especially. Regarding the opponent, he clarified the very important technical details. He asked about the parameters which are important when moving from the lab outside. And what was perhaps the most important, he asked about the precision, which is the key point of this task. And he asked about the dimensions of the setup. However, he did not too much discuss on the turbulent flow and the assumptions behind the simulations. The simulations should not be a black box. The assumptions should be deeply discussed, and this was missing in discussion. And the time was missing, both in the presentation and in the discussion, and time effects are extremely important here. And we would like to highlight some discussion points which were really interesting, such as measuring temperature and the scaling of the system. And for the discussion, we suggest these points, especially the methodology of jitter analysis, experimental setup, and assumptions of the theoretical model.
Thank you.
So
Thank you. So now it's time for the discussion between the reviewer, reporter, and opponent.
Okay, so I would like to start the discussion with the methodology of jitter analysis. It's maybe also a question to the opponent, because when the moving beams were presented, did you notice that the grid behind them also moved? You can show it again if you want. The slide with moving beams. Yeah, because the grid behind them also moves. I don't know if you noticed it, but
Please,
yes.
please, could I explain?
Of course.
Really, it's the point that I should explain, because it's only the it's only the animation, because the animation was made from the screenshots of the video, and it was the mistake of the animating program that that's because the grid moved, that the grid seems to move. And of course, really, we started the camera and the grid didn't move, of course.
Okay, so it was taken before the starting of the measurements, yes?
Yes, of course.
I think they had a little problem to adjust all the screenshots, and that's the only reason.
Oh, okay. So I think we clarified that.
Yes.
And maybe a question to both of the teams regarding the measurements. What kind of laser beam will be better, wide laser beam or narrow laser beam? That's the question to both of you. Okay. Yes.
I should begin. The laser beam, the most important is the parallelity. So we should take the most parallel laser beam as we can, and I think it would be, and if it would be really parallel, the real size of it doesn't influence.
Okay, thank you very much. And how about the opponent? Do you agree with that?
I actually quite don't disagree, because
Okay,
I
why?
think that the wider, the more parallel it can be.
Yes, of course.
Moreover, but there is a limitation to it, and there is an optimum to find, because the wider your laser beam is, the more difficult it is to see your standard deviation.
Yeah, because like between the size and the parallelity, there is the Fourier transform which relates them, and there is the uncertainty principle. So could you please maybe comment on how to optimize the parallelity versus the size of the beam?
How to optimize the
How to find the right compromise between the size and the parallelity? That's the question to both of you.
I think that I should disagree, because I think that the size is less important than parallelity. So I think that we should take the most widest. That if that really that the parallel that the more wide would be the laser point at the beginning, the more parallel it would be the rays. Do you agree? Yes.
Yes.
And
okay, let maybe the
yes.
opponent comment.
Actually, quite yes, but even if your laser beam is not wide enough, you still have a way to increase the parallelism of it by using some lens, and you could know the focal distance of your lens.
Okay, we got a bit of insight here, and also a problem to consider for both of the teams: how to optimize the setup and what can be improved to increase the precision, make the measurements better. That's for both of you, of course. Yes.
I think it's very interesting. I should begin really. I think we should take really the lens. I agree with you, and to make the laser beam as parallel as we could. Also, we can take the mirror in for this. Also, I think that we could optimize the precision of our method by using the slope screen. So the deflection would be greater, and we could easily.
Okay, thank you. Because I noted that there is a remark from our team.
Yes.
Could you show us again the slide where you compare the thermocouple measurements with the optical?
Yes, of course.
So I believe there is a slight misunderstanding here, because I think that the value sigma on the horizontal axis was calculated with the theoretical model.
No, of course no. It was measured.
But in case of the blue points, that measured with thermocouple, did you calculate sigma with the theoretical model?
No, it was only the real. It is only the real temperature for this case. What is really in this graph? Here you can.
Okay, because maybe the opposing team.
I think it's a misunderstanding really. So I would better explain. So on this, the blue points are the measurement with our thermocouple, and for this case, when we measure the temperature with our method, and we get those sigma, and this is the. So we compare the real temperature and the temperature with thermocouple. It's not theoretical values; it's measured values.
Okay, thank you. I think
maybe to the opponent.
Yes, actually, where do your error bars for the thermocouple come from? Because actually it's quite huge. You have almost some tens of degrees for a measurement with a thermocouple.
Yes,
so
that's a good point to
the
consider.
point which I expected, which I wish to discuss, because really this is the temperature distribution on our stovetop isn't uniform. Really, is the construction of the stovetop. So the error bars. The error bars gives us the the distribution of the temperature. So it's the distribution from the
So you mean that when your laser beam is traveling over your plate,
yes,
it will first meet quite edge area
yes.
of the plate, then the center, and then the edge. And you have such huge differences between the edge of your plate and the center of your plate?
Okay,
It's
guys.
really
I
No,
think
I
we've got
think it
some
will be
insight,
important.
but also the other team members can join. So do the teams have any more remarks or questions? Okay, so let's continue since there are no.
Thank you. And so, what do you have to answer to this question? Do you have in
yes,
reality
this is
such huge differences?
really, there are such huge differences between the temperature on the edges of our stovetop and the center of our stovetop. It's the constructive moment of our stovetop.
Okay, so why didn't you try maybe to hit maybe some more little areas? I don't know, in order to, I don't know, with a oven, this kind of things, and to film, to see your laser beam traveling over it, to tend to have a uniform distribution of temperature of your surface.
Yeah,
by
and
hitting
to
it
which
with a
extent
oven.
is the role of heating important here? And
Yes.
what's the maybe question to both of you? What would be the best way to heat the plate so that it gives the ultimate precision of the setup?
I think I thought about it. I think if we could make it, we should heat our temperature. We should heat our surface. For example, with the sun, or with some power source of light. So to get the uniform powerful source of light, to get the most uniform distribution
Okay,
of
and since we
temperature.
are quite a bit short of time, maybe a remark from the opponent about that?
Yes, thank you. Maybe I think that for at least in order to explore the range of temperatures between 0 and something like 200 degrees, you could have tried by putting it in a oven actually. If you put it in the oven long enough, it will be really uniform, at least at the beginning.
Yes,
I
that's
should
also a good proposition. And maybe the final problem to consider for both, is there any minimal temperature of the plate for the jitter to occur?
I'm sorry, there's no time to answer.
Okay.
So, reporter, please conclude in 1 minute.
At first, I would really thank my opponent and my reviewer. At first, the opponent. I thought I liked his improvement points. I think it would really improve my solution. I really think that the analysis of spectrum and the analysis of unsymmetry of the plot would help me to improve the precision of my solution and the precision of my measurements. And I like the discussion. It was really about the measurements. I think that the problem is about the measurements, and we should discuss the optimization of the setup, and we really did this. Thank you very much for this.
Thank you very much. So now we have 6 minutes for questions from the jury. Jean-François Joanny. Yeah, I'm sorry. We need to take one from there.
We have one here.
Jean-François Joanny.
You showed us this Kolmogorov theory, which predicts variations as power laws. Did you try to check directly in your experimental systems if these power laws were verified or not? I mean, did you try to make explicit checks, for instance, by moving the height of the beam or things like this?
To check the quality, the heat, if our heat is, if our quantity of heat is really so. Do you mean that?
No. You showed this CN or CT, and I don't know where they are. The next slide. For instance, there is this 1/z to the 2/3 power.
Yes.
Can you check things like this or not experimentally?
To check the Kolmogorov-Tatarsky model.
Yes, to see whether you can apply it in your experimental situation.
Yes, we did.
And which quantity did you check? I mean, you didn't talk about it.
I mean, we check the spectrum.
The cascade, you check the cascade on top of the heated plates? That's what you did?
Check the cascades. No, we check the spectrum distributions of the length. We check the length scales of vortices from our shadowgraphy.
Who has questions? Okay, we would like a mobile microphone,
Sure.
please.
Okay, I would like to ask a question to everybody, to the reporter, opponent, and reviewer in the kind of captain contest. So please take a chalk and try to answer the question for 30 seconds. And the question is, with the best imaginable setup, with all possible equipment that you can get on the Earth, what is the best precision that you can get measuring temperature?
The number.
Yes, the number, maybe in percent. Like, let's say you have 200 degrees of temperature of the surface. With how good precision you could measure it through the air, having all the equipment that you can have on the Earth. Okay. Just write the number in percents or some uncertainty. 200 degrees Kelvin temperature. And each of you.
Percents.
200 Celsius. Sorry, Celsius.
Percents.
Anything you want.
Yes, yes.
Okay, thank you.
Okay. A small question to the reporter. Did you consider other sources of errors and disturbances that can cause a dispersion, maybe even higher than by temperature convection? For example, if what speed of wind should it there be in order to cause the same effect?
The speed of wind.
Yes.
There was no wind in the room.
Yes, but we're speaking about desert. And did you try to estimate what speed of wind will cause the same turbulence oils with the same effect on the dispersion of this light spot?
It would be. You mean the turbulence with the velocity, not by the temperature? Yes.
Yes.
I think I didn't calculate it, but I think it would be very high. I think it would be about 7 or 10 meters per second.
A short question to the reporter to clarify your work. So did you obtain all your numerical constant in the model from the literature, or do you use your experiment to determine some of them?
We used our experiment to determine the heat transfer coefficient.
Okay, thank you.
My question is mainly for the opponent. You made a remark which I think is very good. That is that in practical situation we would like to extrapolate these measurements down below 100 degrees Celsius. Actually, 100 degrees Celsius difference probably between the plate and the air. So we would like to go much below that. Anyway, in your work, which you had no time to describe. Did you find a method to make measurements for small temperature differences, like less than 100 degrees?
Actually, yes, because we concentrated on upper part of flowing. Also, we also must consider that the Rayleigh number is lower at our temperatures between 10 and 100 degrees. We concentrated on a more laminar flowing on the upper surface of the heated air, and by measuring the speed of these amounts of air rising, we had an experimental dependence of the speed of rising as a function of the temperature of our plate. And so we plotted a quite calibrating curve, which lets us determine the temperature for any on another plate, because we also tested it for several materials.
In one phrase, each of you, please answer this question. Why does the jitter why is the jitter larger for larger temperatures? In one phrase, physically.
Take the microphone, please.
In my opinion, the jitter is bigger for higher temperatures because the higher the temperature gradient is, the bigger the turbulence which causes the jitter is.
Sorry?
Turbulence, yeah.
But turbulence is not large or small. I don't understand. What's the physical quantity that is larger in the turbulence?
Like the fluctuation.
May I? Actually, I think that the bigger the temperature of your plate is, the more complex the movements of the air are, and so locally you will have bigger density fluctuations of your air, so bigger the variations of your optical index, and so you'll just travel over your plate, you meet several little differences like that, one time on the left, one time on the right, these kind of things, and you will have quite random work of your optical variations, and you will tend to have, as she also understood, dependence on the square root of your length. So, and the more the bigger the temperature are, the more the length of your random work unity is. So,
really, I think I could absolutely agree. And really, it was the explanation I heard good. I should only remark that with increasing the temperature, the length scale of vortices decreases. So really, the difference between 2 points in the flow, the difference of temperatures between 2 points in the flow increases, and so the difference between 2 points in the flow also increases. It's a little comment.
Okay, thank you very much to all of you. So now, Dewey, it's time for your marks. And for the next one, we will start just after, because we are very late in time, so... Quoi? Non, non. Ah, si. 5 minutes, mais on sort pas de la salle. Non. Hein? Si, après, on fait les noms. À la fin du troisième. So there won't be any break at the end of this round, because we are very late. Okay, Dewey, are you ready? Yeah, no problem. 3 seconds. So, Dewey, please show us your mark for the reporter team of Russia. So we have 4, 4, 4, 4, 7, 5, 6, 6, 6. Thank you. Dewey, please show us your mark for the opponent team of France, ENS Lyon. We have 10, 8, 8, 8, 9, 8, 8, 8, 9. Thank you. Dewey, please show us your mark for the reviewer team of Poland. We have 5, 5, 4, 4, 8, 7, 8, 7, and 4. Thank you very much. So, yeah. If you could send your grades there, and if you have any remarks, let's start from Michel Spiro.
Yes, I gave 10 to the French team because I found the opponent
both very incisive, right to the point, both in criticism and in suggestions, and very polite.
Sébastien Balibar.
Yes, as shortly as possible. I think that the critical remarks by the French team were very, very good. You identified the weak points of the reporter, and actually I checked that if you had to report yourself, you would have the necessary answers to the questions you asked. So I think your contribution was very good. On the contrary, I found the Russian talk a little disappointing. There seems to be a theory which is applied without verifying that the theory is really consistent with the observation. The remark by Jean-François Joanny saying you have power laws for the dependence on Z and on L, or the width of the plate. Why don't you check that and show us some curve? And the answer was a bit vague, so I was a bit disappointed by that. As for the Polish team, the reviewer, be careful. As a chairman is in an international conference, you don't have to be aggressive, nor to interrupt people before they develop at least a little bit their answer. So I found you a little too authoritarian and a little too much aggressivity in your way of leading the discussion. So that's why I gave you only 4. Somebody else?
Okay, so for the reporter, I think it was a bit disappointing for me. After seeing this this problem played 4 times in the tournament already, like this was not so much improvement. First of all, there were lots of small moments, like all this shaking, all this just presentation problems. The plots were not so perfect. These errors were not so well explained. There were lots of comments where you had to explain what was actually happening because you haven't just technically presented it very well. Then what I would like to comment, first of all, this was one method based only on the oscillation in the X. There is oscillation in time, there is oscillation in intensity. There are lots of phenomena that you can play on, and you didn't go further, you only presented one phenomenon. And the last point, and this point now refers to everybody, and I think this is fail for everybody. Everybody thinks the error of measurement is large. It should be large. You can measure, like here it's like 5% plus minus 10 degrees, even more than 15%. I actually think you can take interferometer and measure it very precisely. And you can extract out of interferometric measurement with very maybe 0.1%, but not like this.
Okay, I will respond to Dmitro. I think for the interferometer we should have a mirror, but it's difficult to go in the desert much far away and put a mirror there. And as for the reporter, I think you should concentrate more on a real situation. You are in a desert and you are looking through this desert, and there are different kind of errors that you should analyze, but you didn't do it. You just focused on your theoretical part. It was good. Shadow imaging was good, but because it was not really applicable into real conditions, and I didn't understand how to apply this, that's what I put you 6. About the opponent and reviewer, I would put you more, but the opponent small fault is that there are some technical points that were raised by reviewer, good points, and you didn't notice it. About the reviewer, you were a little bit playing role of opponent, and that's why 7. Okay, thank you.
Very shortly, in addition of that, for the reviewer, I thought that it was a very good discussion between France and Russia when the opposing team enters the game. And at the end, I'm not sure the reviewer had something in the discussion, and maybe it would have been better if he was not there. No, truly, I'm sorry, but the discussion went in a lot of direction. There was interruption as I speak and so on. So that's why I give you a bad marks. Sorry about that.